5, 4, 3, 2, 1.
I like flying rockets, but I especially like flying rockets high and fast. Today, we're going to look at one way that we can get extra performance out of a regular commercially available rocket motor, and the development and testing that led up to the flight of my most recent rocket, Deft Osprey. This here is a representation of a simple rocket. It has a body tube, a smaller motor mount tube inside, and the motor itself inside that. The majority of high-power rockets are built like this, but if we want to fly higher, the next step is pretty obvious. If we make the rocket just big enough for the motor to fit, we can save a lot of mass and greatly reduce the aerodynamic drag. This is called minimum diameter in high-power rocketry speak, and it's the go-to method for making a high-performance rocket. But what if we want to gain even more performance? We can remove the body tube altogether. This is called sub-minimum diameter, but it still often requires a step in the diameter of the rocket, either to attach a fin can or to couple the nose section to the motor itself. How can we do a submin and still keep a nice smooth outer surface without any steps? We want to be able to attach the fins directly to the motor, and it would be nice if the motor case walls could extend forward so we could couple the nose cone to it without having to attach it on the outside. The method I've chosen to achieve these features is to make a custom composite case for the motor. The process started with small 29mm motors. These were based on Cesaroni Pro 29 reloads. Pro 29s seal against the inside of a flexible plastic liner and have no seals against the case itself, so making composite cases for them is relatively easy. I didn't have to worry about making any sealing surfaces. The design is simple, just the reload in a composite tube, potted in at each end with epoxy, making sure to have enough bond length to hold the closure and nozzle at the operating pressure of the motor. The 29mm motor started with 2 test flights of some 2-grain motors, which both worked perfectly. Here's a cross-section of one of the motors after firing. You can see the forward closure has been pushed down, crushing some of the liner when the ejection charge fired. There are also some voids in the epoxy near the nozzle, caused by using a quite thick epoxy. These are some lessons we can take forward to the bigger motors, but despite these minor problems, the casing itself is in perfect condition. The 29mm phase of the project culminated with my first submin. Brisk Osprey was a 4-grain G400 VMAX. This thing was crazy, and the flight speaks for itself. It took off at approximately 200 Gs of acceleration, but unfortunately took a turn out of the tower and was never found. Importantly though, the motor worked. Next, I pivoted to 54mm motors. The Cesaroni Pro 54 design is a bit more difficult to work with for making a composite case than the 29s. Not that I blame CTI, this is after all not the intended use of their product. It all has to do with the seals. The Pro 54 seals using O-rings between the closure or nozzle and the case itself. The nozzle is glued to the liner, providing some sort of seal at the bottom end, but there is a leak path for gases from the motor to exit the liner at the forward closure. In the intended metal case, this isn't much of an issue, since the aluminum can simply tank more heat, and the gases aren't really flowing past. Ideally, this leak path simply pressurizes the small gap between the liner and the case. With a composite case, however, we don't want any combustion gas anywhere near our case. It can take far less heat than a metal case can. To prevent the motor from burning itself a free bonus nozzle pointing sideways out the top, I added a bead of RTV silicone along the joint here. Ideally, this would be done with an O-ring groove in the closure or an AirTech style forward seal disc, but on the CTI design, the RTV is the only real option. Now, let's build the rocket. This design uses the J760 3-grain motor. It's not crazily optimized. I've given myself some extra recovery and avionics room, and the fins are not beveled. The main goal here is to prove that the motor architecture works, so I can use the design in the future on a longer motor with a more space-optimized design up front to get some serious high altitude. First, I laid up the motor case. This used a drawn-over mandrel stainless steel tube as the mandrel for the case, with a mylar release layer, and the case was made using 4 layers of biaxial carbon fiber sleeving, with Aeropoxy 2032 resin for a bit better heat tolerance. Next, I laid up 1 layer of 6-ounce plain weave carbon fiber on each side of a 1/8 inch thick sheet of G10 fiberglass, which was vacuum bagged. This would become the fins. The nose cone was made using a 3D printed male mold and 4 layers of fiberglass sleeve. It also got a metal machine tip. A coupler was also laid up from fiberglass cloth. I then prepared the shock cord attachment point on the motor after I removed the black powder charge and drilled a hole through the sides of the charge well to feed the shock cord through. The motor was then glued into the casing tube. Plenty of extra laminating epoxy filled any gaps between the liner and the inside of the case, and the ends were potted in with structural epoxy. The epoxy is Mach Bond Thixotropic, which I chose for its strength and heat resistance while still being able to be cured at room temperature. I went with quite a big safety factor on the bond lengths here. The fins were filleted with the same structural epoxy. I also added a couple of temperature-sensitive stickers to see if we might have any signs of the case getting dangerously hot after the burn. I put one sticker near the forward closure and the other near the nozzle. Given the experimental nature of the motor, I decided to put the avionics bay in the nose, so if anything bad happened at the front of the motor, the av bay would hopefully not get barbecued. For my electronics, I had an RRC2 and Easy Mini for my redundant altimeters. For tracking, I used my beta test version of the Silicdyne Reparix GPS tracker and an Elvin beacon for RDF backup. Everything was powered using these small 220 mAh LiPo batteries going through these custom screw switches. Recovery was set up as single separation with cable cutters. Both chutes were custom sewn by me. With some paint on the rocket and the build fully complete, all that's left is to fly.
Rocket in that it is very small and going very fast. This is Noah. His rocket's name is Deft Osprey?
Yeah.
All right. This is a sub-minimum diameter going to 10,000 feet. Very good. On pad E1. All right. Going in 5, 4, 3, 2, 1. Okay,
Motor works, let's go!
Nice and straight. And now the young eyes can claim they actually see something.
I do see a smoke trail. Shut up, altitude 0 meters. A vent, I saw an event.
Yeah, there it is, look at that.
Apogee at 2710. Watching descending.
All right. Range is that cold over on the diesel.
Yeah, we're undershoot for sure.
What a flight! The carbon-cased motor worked perfectly, and the rocket hit an altitude of 9,262 feet and a speed of Mach 2. The acceleration off the pad was about 54 G, and it landed about 900 meters away from the launch rail. Unfortunately, a fin did break off on landing, but this is a single-use rocket anyway, and with a little superglue, it now sits proudly on my high-performance shelf with some other rockets. I hope you enjoyed the video. I've got more cool rocketry projects planned for the future, so stick around for more.